In the previous lecture, we talked about solving second-order linear non-homogeneous differential equations. And we talked about undetermined coefficients method for solving those type of differential equations. We talked about two cases, and now we have case 3. The previous cases that we talked about are if the right-hand side means f of x to be a polynomial of degree n, or if the polynomial is an exponential function. We now have if the right-hand side means f of x, if f of x to be sine or cosine function. If the sine or cosine function, we say yp, which is the particular solution, yh is the homogeneous solution, it's the same. But for yp, we say it equals x to the power r, where r starts from 0, 1, 2. If we have similarity between the choose particular solution with the homogeneous solution, we change r, we start from 0. Okay? X to the power r c sine beta x plus d cosine beta x. Here, the angle is the same. If the right-hand side to be sine beta x, we just say the particular solution to be c sine beta x plus d cosine beta x. Even if the right-hand side is cosine beta x, is the same. In both cases, if the right-hand side is either sine or cosine, we say the particular solution is x to the power r times c times beta x, c times sine beta x plus d times cosine beta x. Here we have an example. We have y double prime plus y prime minus 2y equals sine x. For this function, what we do, we should first find the homogeneous solution. In solving these differential equations, for non-homogeneous differential equations, the first step that we do is finding the homogeneous solution. And for the homogeneous solution, we are going to take the homogeneous part. That means we put 0 for the right-hand side. Yeah? The differential equation becomes y double prime minus y prime, sorry, plus y prime minus 2y equals 0. This is for the homogeneous part. This is for the homogeneous solution. The right-hand side must be 0. And then we write down the characteristic equation. So the characteristic equation is, the characteristic equation is, we replace y double prime by m squared plus m minus 2 equals 0. We now solve this polynomial of degree 2. It's a polynomial of degree 2. We can solve by making two brackets. If you couldn't factorize it, you can use the quadratic law for solving it. Here we say m plus 2 m minus 1 equals 0. This is the factorization of the polynomial. Okay, and here we say we get two different values for m. m1 equals -2 and m2 equals 1. From this bracket, if this equals to 0, we get that m is 1. And from this bracket, if it equals to 0, we get that m is -2. Here we have two different values for m, and we said the first section in this chapter was about homogeneous solution. We said that if we have two distinct values for m, as we have here, we say the homogeneous solution equals, this is, I'm just going to write down the general form of the homogeneous solution for this type. If m1 and m2 are different, you see yh equals a to the power m1x plus b e to the power m2x. This for the case if m1 and m2 are different. We just replace m1 and m2 by their values here. So we get yh equals a e to the power minus 2x plus b e to the power x. This is the homogeneous solution. This is the homogeneous solution. And now we are going to find the particular solution. The particular solution. Up to now, we just solved the homogeneous part and we found the homogeneous solution. And now we try to find the particular solution. For the particular solution, we apply this rule because the right-hand side is a sine function. Since the right-hand side of the function is a sine function, I mean f of x is a sine function, so we use this rule. We use this rule for finding the particular solution. We say, and we start from 0 for r. As I said, we always start from 0. If there is similarity between the chosen particular solution with the homogeneous solution, we try r to be 1 and r to be 2 and so on. Here, for r to be 0, we say yp equals x to the power 0 times c sine beta x plus d cosine beta x. Here, what's beta and what's beta here? Here, for x to the power 0, it's 1. For r to be 0, we just have c sine plus d cosine. So what's beta? Beta is the beta x is the angle of the sine function or cosine function was given. Here, beta is 1. Beta is 1. Beta is the coefficient of the angle. Is the coefficient of x in the angle here. We say from this yp equals c sine x plus d cosine x. This is the particular solution. But here we should find c and d. But let's check if there is similarity between this yp and yh. Is there any similarity? The homogeneous solution is an exponential function. You have two terms, both are exponentials. But the particular solution that we choose is the trigonometric functions. We have two trigonometric functions, so there is no similarity between them. That means we choose r to be 0. Now, here there is no similarity. There is no similarity, so it's okay for the particular solution. Now, we determine the constants. We have c and d in the particular solution. In the particular solution, we must find the values of constants. But for the homogeneous solution, we leave it. If there is any condition, we find them at the end. Okay? But if we have no conditions here, as we have no initial conditions here, that's why in the question we haven't given any conditions, initial or boundary conditions. That's why we just leave the constants in the homogeneous here. We leave them. Okay, to be the same, to be constants. But for the particular solution, we must find the values of these constants, c and d. We must find them. How? From the differential equation. The differential equation is y double prime plus y prime minus 2y equals sine x. Yeah, y double prime plus y prime minus 2y equals sine x. What we do, and we have yp equals c sine x plus d cosine x. What we do, we are going to find y double prime for p, so y prime and y double prime for p. We are going to find these two differentiations of yp for the particular solution. We are going to find y prime and y double prime for p, for yp. Then we replace them into the function. and then we can find the values of C and D. Let's do it. What's y prime? The derivative of sine is cosine. So you get C cosine x. And derivative of cosine is negative sine. So you get minus D sine x. Then for y double prime, we take another differentiation. We get minus C sine x minus D cosine x. We now replace y by yp, y prime by yp prime, y double prime by y double prime of p, yp double prime. Here, in this given differential equation, we replace y by yp, y prime by yp prime, and y double prime by yp double prime. Let's do that. Y double prime is minus, you say put yp prime and yp double prime in the differential equation. We are going to replace y prime, y double prime by yp prime, and yp double prime. Here we have y double prime, so it becomes minus C sine x minus D cosine x, then plus y prime. Y prime is C cosine minus D sine. Then we have minus 2 times y. We just multiply yp by negative 2. If we multiply it by negative 2, we get minus 2 sine x minus 2c sine x, sorry, minus 2d cosine x. It equals to what? Equals to the right hand side of sine x. Now we simplify the left hand side, then we compare both sides. Then we can find the values of C and D. First, let's simplify the left hand side. Here we have minus C sine. First, let's write down all sine terms together and cosine terms together also. This sine term, that sine term, and this is sine term also. Okay, we have these 3 sine terms. We have minus C sine x minus 2c sine x means minus 3c sine x minus 3c sine x, then minus d sine x, and between these two we can take sine as the common, is it? We can write down as minus d all sine x. This is for the sine terms. And then for cosine terms, we have minus d cosine x, c cosine x, and also minus 2d cosine x. Minus d, minus 2d is minus 3d, minus 3d cosine x. So let me write down beside of it. Minus, let's see, plus, minus 3d cosine x, then minus, so plus c cosine is the c, yeah, I forgot to write down c here. This is c cosine x plus c cosine x, and between these you can take cosine as the common, so we get minus 3d plus c cosine x equals to what? Equals to sine x plus 0 cosine x. Since only we have sine, that means the coefficient of cosine is 0. That's why you have no cosine. Okay? We have 1 sine x plus 0 cosine x, since you have no cosine in it. Now, we just equal the coefficients of sine to each other and coefficients of cosine to each other. We say minus 3c minus d minus 3c minus d equals to what? equals to the coefficient of sine in the right hand side. What's the coefficient of sine? It's 1. In the right hand side, yeah, the coefficient of sine is 1. بردمي ساين تشيل يا راس. بردم كان ساين كم بيك. بردمي ساين number جوبر. Cosine number جوبر. Okay. So the coefficient of sine the right hand side is 1. We equal this to 1. And also we have cosine. Minus 3d plus c equals to what? Equals to 0. Now we solve these two equations. We solve these two equations. You can solve it by simultaneously, I mean, by substitution or elimination. Yes. Yes. You can't find any of them first. Let's first from this equation, let's say this equation 1 and the second one to be equation 2. This is a linear equation. From this equation, we say C equals 3D. Is it? Then put in 2. Put in equation 2. That means you replace C by 3D. And you get minus 9D minus D equals 1. Is it? We just replaced C by 3D in equation 1. This equation 1. So in 1, not 2. Equation 1. This is equation 1. If we replace C by 3D, we get minus 3 times 3D, which is minus 9D. Yeah. So from this, D equals 1 over 10, minus 1 over 10. It's minus 1 over 10. This is D. How about C? We said C is 3 times D. So C equals minus 3 over 10. Is it? Because C is 3 times D. D is minus 1 over 10. If you multiply by 3, we get minus 3 over 10. This is C. So the particular solution is, we said the C sine plus D cosine. We said C sine plus D cosine. It is minus 3 over 10 sine x plus, and becomes minus 1 over 10 cosine x. This is the particle solution. Now we have both particle solution and homogeneous solution. The above one, this is homogeneous solution. And this one which we find now is the particle solution. We say Y, which is the homogeneous solution, which is the general solution, which is the final answer. Y is YP plus YH. It equals minus 3 over 10 sine x minus 1 over 10 cosine x, then plus the homogeneous solution. So what was the homogeneous solution? The homogeneous solution is A e to the power minus 2x plus B e to the power x. This is the final answer. This is the general solution. We don't need to find it, but if we have given initial conditions here, for example, here, if we have given y of 0 equals 1 and the y prime of 0 equals 0. At this case, we are going to find the values of A and B here. Okay? We are going to apply these two conditions here to find the values of A and B. Okay? Yes. Yes. لا فرق يا حل دوم حل السيام كيسي دوم exponential function وياك in معنى all are the same process. But in the first case, we said we are going to choose a polynomial. In the second case, we said we are going to choose an exponential function. But for the third case, if the right-hand side is a sine or cosine function, we choose C sine plus D cosine. Okay. If there is no similarity, if there is similarity, we choose x times cx, C sine plus D cosine. If there is still a similarity, we choose x squared, C sine plus D cosine. The same process. All are the same process. First, we are going to find the homogeneous solution. Then we choose the appropriate particular solution. It depends on the right-hand side. If it's polynomial, if there's exponential function, and if there's a trigonometric function. We are going to choose appropriate one. Then we are going to find the derivatives. We return them to the given differential equation to find the values of constants. After finding the values of constants, we get the particle solution. And we found the homogeneous solution in the first step. We just find the sum of them. That's the result. Okay. Now we have the fourth case. Case 4, if we have the sum of the previous cases. In the previous cases, we talked about polynomial, we talked about exponential function, and we talked about the trigonometric functions. If the right-hand side to be either sine or cosine, or both are the same. Okay. I mean, if we have the sum of those three cases here, we have more than one particle solution. If we have two cases, if we have exponential with polynomial, in this case, we have two particular solutions. So here we must find two particular solutions. If we have three of them, all of them, I mean, we must find three particular solutions. Let's try this. Here, as you see in this example, we have e to the power minus x plus x. Here you have two cases in the right-hand side. F of x is the sum of two previous cases. This is polynomial. This case one, let me write down case 1. And this is case 2. We have two cases. In this case, if we have more than one case, we should find two particular solutions. But for the first step, it's the same. We just find only one homogeneous solution. Here, for the homogeneous solution, we are going to take the homogeneous part. That means we are going to put 0 for the right-hand side and we solve it by finding the characteristic equation. Let's first find the homogeneous solution. For the homogeneous solution, we say y double prime minus y prime minus 2y equals 0. We put 0 to the right-hand side, to f of x. Now we write down the characteristic equation. We say it is m squared minus m minus 2 equals 0. Now, if you could factorize this, we do it. Okay. So the factorization of it is equals 0. Here, m by m minus 2 plus 1. We get this. This is the factorization of the above polynomial. Now, how many values of m do we get? 2. We get 2 different values for m. What are the values of m here? m1 equals 2 and m2 equals -1. We have these two values. They are different. Since they are different, so we say yh equals a e to the power m1x plus b e to the power m2x. And so it equals a e to the power 2x plus b e to the power minus x. This is the homogeneous solution. This is the homogeneous solution. Okay. Now, to find the particular solutions. Here, in this case, since the right-hand side is the sum of two cases, so you must find two particular solutions. One for the exponential part and one for the polynomial part. For the exponential part, we say yp is yp1 plus yp2. First, for yp1, let's work on the exponential part. Let's work on the exponential part. So what's the particular solution for exponential functions? If f of x to be an exponential function, we say, look, this is e to the power minus x, e to the power minus x. We say the particular solution is a constant times e to the power minus x. If there's any other number here, let's say if you have 5, we just say it's, let's say c e to the power minus x. This is the particular solution that we choose. Okay, but here it's 1. So we say for yp1, you see let yp1 to be c e to the power minus x, and let's check this is for r to be 0. That's for r to be 0. We say the general form for exponential functions, it is x to the power r, c e to the power mx. M is this one, is this value. M is -1. So just write down the same. It must be the same exponent as it's given in the example, mx. Here, for r to be 0, we have only c e to the power minus x. Let's check if there is similarity between yp1 with the homogeneous solution. This is the homogeneous solution. And this is yp1 that we choose. Is there similarity between them? Yes, because we have e to the power minus x the same. And it's multiplied by a constant. B is a constant, and here c is a constant also. E to the power negative x and e to the power negative x are the same. That means there is similarity. Similar to YH. It's similar to YH. So we choose for R to be 1. We choose R to be 1. Then the particular solution yp1 becomes x c e to the power minus x. This is yp1. Is there similarity between this yp that you write down here with the homogeneous solution? Do you have any term in the homogeneous solution, which is x multiplied by an exponential function to the power negative x? No, we have not. But here we have x. Okay, here we have x. That's the same. That's the difference between them. It's x multiplied by an exponential function to the same exponent. So that's why they are not similar. So this is the particular solution that we choose. Now, what we do the same process as we did before. We are going to find the derivatives, and then we'll return them to the given differential equation to find the value of constant. Now, from this, yp1 prime. Why do we say yp1 prime? Yp1 because here the right hand side you have two cases. So for each of them, we should find the particular solution. For y prime p1 equals, we find the derivative of this function as a multiplication of two functions, x times e to the power negative x. We say first times derivative of the second plus second times derivative of the first. First times derivative of the second is minus x c e to the power minus x plus second times derivative of the first c e to the power minus x. This is why yp1 prime. For yp1 double prime, we are going to find derivative of the first derivative. We are going to find derivative for this one to get y double prime. For the first term, we say we have multiplication of two functions. We have x times e to the power negative x. And here we say first times derivative of the second plus second times derivative of the first. We get x c e to the power minus x minus c e to the power minus x. Then here we get minus c e to the power minus x. This is derivative of that one. The last term, the third term, is the derivative of the second term of the above one. Now, we have both f prime and f double prime. Then we put these into the given differential equation. We put this, we say put yp1, yp1 prime, and yp1 double prime into the given differential equation. Okay, now what we get? This is the differential equation. Y double prime minus y prime minus 2y equals e to the power negative x. We ignore the other case. We ignore x. Okay, we just use the case that you worked on. So we ignore x here. We just use e to the power negative x. Y double prime minus y prime. Here we have y double prime minus y prime minus 2y equals e to the power minus x. We don't use this part, okay? Because we worked on the exponential part only. We don't need to write down that part. Now, we say y double prime is x ce to negative x. And it could be simplified more. We get x ce to negative x minus 2 ce to negative x. And this is y double prime. We say y double prime is x ce to negative x minus 2 ce to negative x. This is y double prime. Then minus y prime. Y prime is minus x ce to negative x plus ce to negative x. Let me write down bigger. So we said y double prime is x ce to negative x minus 2 ce to negative x minus y prime is minus x ce to negative x plus ce to negative x. Then plus minus 2 times y. Minus 2 times y. What's y? Y is yp1, which is x ce to negative x. And equals to what? Equals to the right hand side, which is e to the power negative x. Now we are trying to find the value of c here. Okay. Sorry. No. First, let's enter this negative sign into the bracket, and also this negative 2 into the bracket. We get minus x. Sorry, you get x ce. We get x ce to negative x minus 2 ce to negative x plus x ce to negative x minus ce to negative x. I have just entered this negative sign into the bracket, and to enter this negative 2 into the bracket, we get minus 2x ce to x to negative x. It equals to e to negative x. Look, here we have x ce to negative x, and x ce to negative x means 2x ce to negative x. With minus 2 x ce to negative x, these are cancelled out. Now we have minus 2 ce to negative x minus ce to negative x. It means we have minus 3 ce to negative x equals to e to the power negative x. These two are cancelled out from both sides. We get minus 3c equals 1. That means c equals minus 1/3. This is the value of c. Is it? Okay. So now we write down the particular solution. So yp1 equals to what? Minus 1/3 x e to the power minus x. We just replaced into the particle solution, this yp. This is the choose yp1. That's for yp1. And then for the other part, for x, we do the same procedure. But for polynomials, we say for yp2, let yp2 to be, we said if the right hand side is a polynomial, let's say if f of x to be x squared, then the particular solution that you choose here in this case, we say it equals ax squared plus bx plus c. So what if the right hand side is only x? We say it is ax plus b. Here, because it's degree 1, we just write down a polynomial of degree 1. We don't need to write down a degree 2 polynomial. That's why. Here, we are going to find yp2. For yp2, we let yp2 to be, this is for r to be 0. That's for r to be 0. We say yp2 as this is dx plus e, because we used a, b, and c before. That's why we don't use repeated constants. Now we have dx plus e. Then, is there a similarity between this with the homogeneous solution, with this one? No. There is, because here both terms are exponential functions, but here we have a polynomial function. They are different. Since there is no similarity, that means here we have no similarity. No similar terms with YH. So now what we do, we are going to find the derivatives, then return them to the differential equation. yp2 prime equals to what? Equals d. Then y double prime of p2 equals 0. Then put yp2, y prime p2, and y double prime p2 into the differential equation. So what's the differential equation? The differential equation is y double prime minus y prime minus 2y equals x. We just write down the right hand side. I mean the right hand side for the second part. Okay, we found for the first part, for the first case, we don't need to write down exponential function. We just need to write down the polynomial one. Okay, and so this is the differential equation. And then we get y double prime is 0 minus y prime is d minus 2y is dx plus e equals to what? Equals to x plus 0. The constant term is 0 here. Now we have minus d. First, let's introduce negative 2 into the bracket. We get minus d minus 2e minus 2dx. Here, these two are constants. These two are constants. And this is the coefficient of x. It equals to what? Equals x. And then by comparing them, we say minus 2d equals to what? The coefficient of x equals the coefficient of x. That means minus 2d equals to 1. As we have 1 to the coefficient of x in the right hand side. This is 1. That's why we say this coefficient was minus 2d equals to what? Equals to this coefficient. and coefficient of x squared equals to the coefficient of x squared. The constant term equals to the constant term, but here we have no constant term in the right hand side, so that's why you say minus d minus 2e equals 0, and from this you say d equals minus a half, and also minus d minus 2e equals 0. Putting this into the second equation, what we get, if d to be minus a half and return it to here, we get minus 1/4. E equals minus 1/4. Do it by yourself, okay? Try to find by yourself. That's minus 1/4. Sorry, 1/4, not minus 1/4. It's minus become positive, and then it becomes 1/4. Yeah. This is 1/4. That's d and e. So how about yp2? yp2 is equal to what? Equals to cx, sorry, dx plus e. It's dx plus e. What's d and what's e? We found them. d is minus a half and e is 1/4. So it is minus a half of x plus 1/4. This is yp2. So now we found yp1, yp2, and yh. And we said that the general solution is the sum of all yp's with a homogeneous solution. yh equals yp1, y of x is yh plus yp1 plus yp2. This is the homogeneous solution. This is yp1 that you found, as you see here, this yp1. Then yp2 is minus a half of x plus 1/4. That's yp2, which we found. Okay. So that's the solution of this type of questions. Let's take a break. We now have solving higher order linear ordinary differential equations. Up to now, we talked about those differential equations which are order 2. I mean, we just talked about second order linear ordinary differential equations. But now we talk about solving higher order linear ordinary differential equations. That means if you have, let's say, order 3, order 4, and so on, any order of differential equation. For order 3, for third order, we say this is the general form of equation of the third order linear ordinary differential equation. Here's the same as the previous. If f of x to be 0, we just have homogeneous solution, and it will be the general solution. But if it's not 0, we have those 4 cases that you talked about. It's either if this polynomial, if it is exponential, if it is trigonometric function, or if it is the sum of those previous cases. We have those 4 cases for particle solutions. The characteristic equation for third order linear differential equation, we replace y triple prime. Here we have y triple prime, ay triple prime, a3, plus a2 y double prime, plus a1 y prime, plus a0 equals 0. We replace y triple prime by m cubed, and we replace y double prime by m squared. This by m, and this is by only the constant ay. Here we have a0 y. We just have the constant there. So this is the characteristic equation. For this equation, we are going to find the values of m, m1, m2, and m3. Since that's a polynomial of degree 3, that means we have 3 different values, 3 values for m. We say the homogeneous solution depends on the values of m. If m1 doesn't equal to m2 and doesn't equal to m3, that means if they all are distinct, then the homogeneous solution equals a e to the power m1x plus b e to the power m2x plus c e to the power m3x. But before, we just have these two. We said it's a e to the power m1x plus b to the power m2x. That's for two distinct roots for the characteristic equation if the differential equation is second order. But if this third order, we have 3m. If they are different, if they are distinct, we say the homogeneous solution is a e to the power m1x plus b e to the power m2x plus c e to the power m3x. This is the homogeneous solution. That's the general form of the homogeneous solution. If they are equal, if they all are equal, before we said if m1 equals m2, that's for second order linear differential equations. We said if m1 and m2 are equal, then the general form of the homogeneous solution is yh equals a e to the power x plus bx e to the power x mx. This is for second order. How about third order? If m1 equals m2 equals m3, here you say plus c x squared. Look, we just increased the power of x by 1. E to the power mx. That here, in this case, all all roots of the characteristic equation are equal. Yeah, it's written down here. If m1 equals m2 equals m3, then it equals a e to the power m1x plus bx e to the power m1x plus cx squared plus e to the power m1x. That's taken as the common between the terms. This is the homogeneous solution for equal roots of m. I mean for the characteristic equation. Now, if you have two equal roots and the third one is different from the previous two roots, we say the homogeneous solution for the equal ones is a e to the power m1x plus bx e to the power m1x. Then for the third one, we have c e to the power m3x. For this one, we are not going to put x because it's different from the other two roots. But if we have two of the roots to be complex roots and one of them to be a real root, then for the real root, we say it is a e to the power m1x. But for the complex ones, we say it equals to e to the power alpha x, which is the real part, plus minus I beta. Here it becomes c cosine beta x plus d sine beta x. This is the homogeneous solution for this type of roots for the characteristic equation. So you have these four cases for finding the homogeneous solution of third order linear differential equation. And for fourth order, it's the same. If they all are distinct, we say it is a e to the power m1x plus e to the power b e to the power m2x plus c e to the power m3x plus d e to the power m4x. But here, for the characteristic equation, we say we replace y to the y4 primes by m to the power 4, y triple primes by m cubed, y double prime by m squared, and y prime by m. Okay. If the characteristic equation has four different roots, four different real roots, we say the homogeneous solution is in this form. If the roots are real and equal, if they all are equal, we say it equals a e to the power m1x plus bx e to the power m1x plus cx squared e to the power m1x plus dx cubed e to the power m1x. This is the general form of the homogeneous solution for that differential equation, which has different roots for the different solutions for the characteristic equation. If you have a combination of two equal roots and two distinct roots, for the distinct roots, we just say a e to the power m3x plus b e to the power m4x, and here it's given as c and d. But for this one, as these are equal, we say m1 e to the power m1x, a e to the power m1x plus bx e to the power m, because you have two repeated roots. That's why we say a e to the power m1x plus bx e to the power m2x. But for others, we have different ones. M3 and M4 are different. We say M3 for M3, since it's different from M1, M2, and M4, we say it is C e to the power M3x, and for M4 also D e to the power M4x. You have these solutions for that case. Now, if we have the combination of equal and complex roots, if M1 equals M2, but M3 and M4 are complex numbers. In solving this characteristic equation, we get four roots. Or we get four values for M. We say, in this case, if two of them are equal and the other two are complex numbers. For the equal ones, we say a e to the power m1x plus bx e to the power m1x or m2x. Therefore, the complex one, we have sine and cosine. We say e to the power alpha x, which is the real part, times c sine or c cosine plus d sine beta x. So it's cosine. The second one is, the first one is cosine. Yeah, one of them should be cosine. One of them, okay? Either the first or the second one should be cosine. This is the solution. As you see, this is for the equal ones, and these are for the complex ones. And the last case, if we have two non-equal roots and two complex roots. For the non-equal ones, we say a e to the power m1x plus b e to the power m2x. In this case, I'm not going to multiply by x. Okay? I'm not going to multiply the second one by x. Why? Because these are different. In only the case if the roots are equal, then we add x. And here we have a complex one plus e to the power alpha x times c sine beta x plus d cosine beta x. That's all. Habibi Sani. See? No, I'm please not happy. I'm azan bo complex shona. Why? Azan bo do jiawazi shona. Duani jiawaz. Vale. Abi Ama que se can crescer basma. Let's return to the previous. Look, we say let's go to the homogeneous one. Yeah, that's it. We say if m1 doesn't equal to m2, this is the solution. These are for distinct. This is for repeated roots. Yes, that is in the beginning of chapter 2. Now we have some more. We have variation of parameters also, and also applications of second order linear part in the differential. Sorry, we have 2 more weeks for this. No, we have only 1 more week for this chapter. We should finish by next week. Yeah, we finish it. We finish it. So it's enough for today.